pipeline will work at its best. And so TDA is one way to get these features from data. And the particularity of this pipeline is to have an intermediate step which computes invariance. In this talk, invariance will take the form of barcode or generalizations of barcodes. So just to give you some motivation, so just I wanted to show you one example of application. I'd like to show it because we really see the impact of using TDA in the context of data analysis. So what is this application about? It's about segmenting 3D objects, for instance, digital models of airplanes or of animals or humanoids, from examples. Okay, so you're given a few examples, and then you want to train a machine that, given a new shape, will be able, on its own, to segment the object into its natural parts, so to speak, where natural really comes from the examples that you have. And so to do this, the classical technique is to take the object and extract features, so transform the object into vectors, and then feed a classifier, so a learning algorithm with these vectors. And then this learning algorithm, you can use then, given any test shape, you can use the algorithm to predict the label for each part of the shape. Easy to segmentation. Now, what we did in this example is that the features that we generated were obtained from TDA, so it looked like barcodes, like you see here, and we fed our predictor with these barcodes. And I want to show you the table of results. So we trained one predictor per class, so there were several classes of 3D objects, so there were humanoids, there were airplanes, ants, and so on. For each class, we trained on a few examples a predictor. And we trained it with several batches of features. The first batch was derived from TDA. The second batch was derived from features from the field of geometry processing. So those features are based on statistical or geometric quantities. And then we trained the classifier with both batches at the same time. And the numbers that you see here are the error rates of the classifier or the predictor on the test shape. So as you can see, the error rates that you get by using TDA features or normal features, so to speak, are more or less equivalent. They're in the same order of magnitude. But the interesting part is when you combine the two sets of features, you actually get error rates that drop by a factor of half or more. And so what this tells us is that the features that TDA generates are complementary to the features that exist from the expertise from the field. Okay. And so this is very interesting for practitioners because it really shows to them that TDA can really bring a complementary type of capture a complementary type of information. Okay, so what is the principle? The principle is it's inspired from Morse theory, so it's something that has been out there for a while. So the principle will be the following. So you have your data set here, a point cloud in the plane. And what we're going to do is from this data set, we're going to build an object, a topological object, which will be a filtered topological space. So it's a family of topological spaces that are nested. And this family here will be indexed by the real line. Okay. So in this particular example, I'm choosing a family which will be just a collection of balls of the same radius around the data point. So for instance, for t equals 0, then the collection of balls is just the collection of the points. And then as t increases, you see the radii of the balls grow at the same rate. And therefore, the union of balls grows. Of course, this way I get a family of unions of balls that is nested for any t and t prime. Ft is always including t prime when t is smaller than t. And then what I'm going to do is I'm going to use homology to track down throughout the family the evolution of the homology groups of this union of balls as t grows from 0 to plus infinity. And what I claim is that when you do that, you can decompose the object that you get at the algebraic level. So I'll come back to this right afterwards. In a way that you get a barcode, one for degree 0, homology degree 0, so connected components, one for homology degree 1, and likewise, you would have a barcode for homology degree 2, degree 3, and so on. And so this barcode allows us to track down the evolution of the topology within this growing union of balls. And this is the basic way to obtain barcodes from data. Yes, here you will get, it's more than the Betti numbers, because you see, if you computed level-wise the Betti numbers, you wouldn't know how to connect the homology groups together. So we're extracting more information than just the Betti number. So here I give an example where I'm using just a union of rows, but you can use a sub-level sense of arbitrary functions. In particular, in practice, people like to use density estimators, they like to use projections or distances in general. And there's a whole zoo of functions that you can use. There's a lot of code out there, and there are a number of libraries that you can try out to play out with this construction. And the standard library now in TDA is called Oudot. It's maintained by our research. So at the algebra level, what's going on? So we start out from this filtered space here, and then we apply homology with coefficients in the field. And so this collection of topological spaces connected by inclusions becomes a collection of vector spaces connected by linear groups. And this is a module over a certain algebra, so we call it a persistence model. And generally speaking, for us, a persistence module will be given a poset P and a field K is going to be just a functor from that poset to seen as a category to the vector spaces over K of finite dimension. And among all these functors, some of them will be of particular interest. We call them the interval modules. So these are indicator modules of intervals. Okay, so an interval in the poset is defined as being a convex connected subset. Okay, so for instance, if you take the poset R2 with the product order, then you would get an interval. An interval would really look like this. It would look like a band in between two staircases with that. And the corresponding indicator module has, of course, spaces equal to 0 outside the interval and equal to the copies of the field inside the interval connected by identity maps. So it's very important for us to have these to work with these so-called interval modules because they're really easy to represent on the computer because we have applications in mind. And so we need to work with things that we can easily represent on the computer and that we can easily manipulate. And in particular, if you give these interval modules to a user, it can help him interpret what's going on. In the same way as in the one parameter case, the intervals are regular intervals of the real line, and it's easy for a user to interpret what's going on. So he knows that, for instance, this interval will correspond to a hole that would appear at level maybe 13. And that would die around CL equal to 20, okay, around level 20. So in the same way here, you want to be able to give interval modules to the user to interpret the structure of the module. Okay, so these are really the objects we will be interested in. So in the one parameter case, we know that persistence modules are always decomposable as in two direct sums of such interval modules. And this is where the barcodes come from. Okay, so you always have a direct sum decomposition of the module, and these interval modules have local endomorphism ring, and therefore the decomposition is essentially unique. Hence the well-definedness of the barcodes. They exist and they are unique. Let me say that there are two cases that are of interest in practice. The first case is when the poset is finite. This is for computations. When you want to do computations on the computer, you need to work with a finite poset because otherwise you can't represent things on the computer. And the second case is for what we call the continuous setting, where the poset is the real line itself. Okay. So you have to imagine that in practice there is maybe some physical phenomenon that you want to model, and you have a sampling of this physical phenomenon, and the physical phenomenon has works maybe on a continuous phase space, and so there will be a continuous filtration that exists out there, and it has a corresponding barcode. You don't have access to it because you're only taking measurements. What you have access to is a finite sampling from which you build a finite filtration, and from which you get a barcode. And of course, in practice, the question will be, will the barcode from the finite sampling converge to the barcode of the continuous underlying object, and if so, at what rate, and so on. So you see, for the calculation, you have finite objects, and for the analysis, the mathematical or statistical analysis, you need to manipulate as well the modules that are indexed over continuous process. So, okay, so you see, this is where the barcodes come from, but in the context of data analysis, it's important to have features that are stable, in the sense that if you perturb your data a little bit, you need the features to be perturbed just a little bit. This is because otherwise, you will not be able to say anything from a statistical point of view. Okay, because if you change a little bit the measurements and then suddenly your features blow up completely, it will be very hard for you to ascertain that what you're seeing is really signal and not just artifacts. Okay. And so what's interesting with this mathematical framework is that we do get a notion of stability of the barcodes, and it's expressed as follows. So on the category of functors from the real line seen as a coset to the finite dimensional vector spaces, we can put a metric, which is called the interleaving distance. So where does this distance come from? It comes from a kind of a relaxation of the notion of isomorphism. So say I take two modules, M and N, indexed over R, and I'm going to say, of course, that these two modules are isomorphic if there are two morphisms, one from M to N and one from N to M, such that the following diagram predicts. Now, how can I relax this definition? Well, just as follows. I'm going to say that there is an epsilon interleaving between the two functors or the two modules, if and only if there are two morphisms, phi and psi, that take N not to N itself, but to a slightly shifted version of N, and that take N to a slightly shifted version of N, where the shift is given as follows. So the shift takes the module and basically shifts it in the indices. It shifts it upwards in the indices by epsilon. This is a well-defined functor on the category of persistence modules. And so you really want the existence of these two morphisms between N and N epsilon and between N and N epsilon, such that the following diagram here comes, where the morphisms, the natural transformations that you have here, are the natural morphisms that exist between a module and its shift. There's a natural transformation from a module and its shift. So here's an example where my module is just an interval module. The effect of the shift is to move the interval leftwards by epsilon, and then there is a natural morphism from M to M epsilon. It's just the identity over the overlap between the two intervals, and which is 0. Okay. And why is this diagram an epsilon relaxation of the one at the top? Just because if you let epsilon go to 0, you get back this small diagram. So this is, yes? I'm sorry? The distance can absolutely be infinite, yes. Yes, it's an extended distance, and in fact, it's only a pseudo distance. There are modules that are at distance 0, but not isomorphic, because the distance is defined as an infimum of the epsilons over for which there is an epsilon interleaving. So in particular, there are some modules that are non-zero and that are nonetheless at interleaving distance 0 of the 0 module. Okay, so why is this distance interesting? First, for two reasons. The first one is that it gives stability. So if I start from two functions from a space X to R, and I take the family of their sublevel sets, as in Morse theory, and then I apply homology to each one of them. So capital F here is the functor that to every real number associates the sublevel set to any real number T associates the T sublevel set of F. And likewise for capital G. Then I post-compose by homology. And then I have this inequality. So the interleaving distance between the persistence modules obtained from these two functions is bounded above by the difference, the supremum norm of the difference of the two functions. And more importantly, so first of all, we get stability from this definition of interleaving. And then there is a result that says that the interleaving distance is actually universal in the sense that it's the maximum distance that you can put on the category of persistence module that will give you this stability. So for any other distance that will give you stability with the same constant one here, we always have that the other distance is bounded above by the interleaving distance. So it's the most sensitive distance among all the stable distances. This is why we consider that it's a natural choice of distance for the category of persistence. Now, you can't work in practice with this distance on a computer because computing it will require you to look at all possible pairs of morphisms. So that's like a problem that you can't solve on a computer. But fortunately for us, actually the distance factors out in the following sense. We will say that a pair of morphisms is a bottleneck epsilon isomorphism if not only do we have this commutative diagram, but also the morphisms phi and psi factor through the direct sum decompositions of elements. So if we start out with two modules and their direct sum decompositions into interval modules, then epsilon interleaving, bottleneck epsilon interleaving will occur if the two morphisms phi and psi under consideration factor through the decompositions of elements. So what that means in terms of summands, it means that really you can find a partial pairing between the summands of n, which are in blue here, and the summands of n, which are in red, such that the intervals that are paired are within distance of each other, in the sense that you have to move the endpoints by no more than epsilon to match one interval onto the other. Of course, you may have some summands that are unmatched, but these summands have a length that is bounded by 2 epsilon. And so in the same way, the bottleneck distance is the infimum of the epsilons for which there exists a bottleneck epsilon isomorphism. And you can compute it, because if you have the decomposition into interval summands of each of the two modules, then this is just a matching problem, and computer scientists know how to solve it very well. So it becomes a combinatorial problem. What is the relationship between the two? Well, obviously, the interleaving distance is bounded above by the bottleneck distance, because of course, we're adding one extra condition on the bottleneck interleaving. And in fact, the two distances turn out to be equal. Okay, so that's really what saves the day for one parameter persistence when you're talking about the distances. It's that these two distances are actually the same. And so you can compute the interleaving distance via a purely combinatorial problem. Okay, so to wrap up, in one parameter, we have all that we could wish for. First of all, we have structural theorems that give us a complete classification of the persistence modules via their barcodes. We have efficient algorithms. I didn't talk about this, but we have algorithms to compute them, these barcodes. And we have the isometry theorem that I just talked about that tells us that, first of all, the barcodes are complete, not only algebraic invariant, but also metric invariants for the category of persistence modules. And this gives us a combinatorial algorithm for distance computation. But also, you can then see the space of persistence module as a space of measures. Because basically, these barcodes you can see as discrete measures. And there's a way to represent them as diagrams of points in the plane, which is called persistence diagram. And then these diagrams are just like discrete measures in the plane. And so you can really see the space of persistence diagrams as a space of measure, and you can study it. You can study its metric curvature. You can start doing statistics in that space, and you can also do machine learning. So this is great. Just a few words about the history. So as I said at the beginning, the intuition, the inspiration goes all the way back to Morse theory. And in fact, Morse himself published a paper in 1940 where he really introduced the notion of persistent homologism, topological persistence in one parameter. This paper is called Rank and Span in Functional Topology. And basically in this paper, ranks are intervals and the spans are the lengths of the intervals. Then the idea has echoed in a number of subsequent work. So in spectral sequences, for instance, spectral sequences are a way to compute the persistence barcode associated with persistence models. Then later on in the 1990s, there was a theory that was developed by some Italian groups, which is called size theory, which reinvented, so to speak, this theory in the special setting of homology in degree 0. Then there are the canonical forms, which are another way to another name for persistence diagrams, which were introduced by Sergei Varenko in the 1990s as well. And then at the end of the 1990s, Vanessa Robbins introduced the persistent eddy numbers, which are again another way to define the persistence. I think it's the one. I mean, are there more than one derivatives already? Oh, I don't know which one. I'm sorry. Yeah. Okay, so then I don't. Now, the current instance of the theory was really phrased at the turn of the 21st century, where Edelsbrunner and Al from Duke University introduced the persistence algorithm to compute persistence barcode. And Carlson and the Warden coined the name persistence module. And then the notion of interleaving came a little bit later at the end of the year 2000. All right, so now let me move on to multi-parameter persistence, where, as you would imagine, we're going to use not a family of topological spaces that is indexed by more than one parameter. So why would we want to do that in the first place? So there are two good reasons to do it. First of all, in some problems, you may have not just one variable that you are interested in, but several variables. If you think, I like to give the example of a medical application when you want to study the effect of a treatment. In fact, the effect of a treatment can be measured by two quantities. First of all, its efficacy, how much it helps cure a disease, but also its risk. It may have side effects. And you really want to study the impact of giving this treatment to a patient through these two variables. Okay, and you really want to study their joint effect. So you want to study the joint variable. And the second reason is that more generally, since we're looking at sublevel sets of functions, and we're basically throwing away all the geometry. We're keeping only the homology. So this is a very weak invariant. So we're keeping just very little information about what we have initially. And it's very easy to come up with, for instance, metric spaces that are not isometric to one another, but nonetheless, the features that you get, the barcodes that you get, are the same. Okay, so the barcode itself will not be a complete invariant of those metric spaces. But now the magic is that if you start using more functions than just one function, eventually you might be able to discriminate between various metric spaces. And here's an example of a contribution that I found very interesting, which is around the years 2015, which said the following. So suppose I am interested in the subanalytic compact subset of RD. Okay? And I want to discriminate between them using TDA. So how am I going to do that? Well, what I could do is take as my function, I could take, for instance, choose a direction and take the projection along this direction. So then my filtration would be just the sublevel set of that projection. Okay, so we start from the empty set, and then I would have like maybe this part here and it would roll. If you do that, then of course it's easy to build two complex analytic subsets of RD that will have the same barcode, but which are different nonetheless. Okay, but now if I let the direction range over all the sphere of direction, and then if I collect all the persistence diagrams that I obtained this way by this construction, then in fact the transform that I'm building is injected in two different compact sets, and subanalytic subsets will give me two different collections of barcodes.
Are you making Oudot construction?
Yes. And the results, I mean, this is the result that I talked over and over, which uses your version.
Because why do you say it's injective? It's bijective.
I mean, I see the transform from the collection of all compact subanalytic subsets of RD to the collection of all compact subsets of the barcode space. I'm not seeing it as a space of constructible functions. So that's why I'm saying this particular one is injected. Of course, if you take the currently indicator functions, see them as constructible functions, then you will have a bijective. Okay, but of course here we're using an infinite number of functions because of course W, the direction ranges the whole sphere, and of course on the computer you can't do that. And so the hope is that by instead of collecting all the persistence barcodes independently, we might want to study the joint effect of several directions. Maybe by studying the joint effect of several directions, we might be able to use fewer directions than just collecting the diagrams, computing independently. So that's the hope. So the mathematical formulation is the same as before, except that R is replaced by R to the D. And again, there are two instances: the finite or discrete setting, where we start out with a poset that is a finite grid, or that is maybe Z to the D, and the continuous setting, where the poset is R to the D, again equipped with an order, which is the product order. Okay, so X is less than Y if Xi is less than Y, like Yi for every. And in this context, the persistence modules are again counters from these posets to finite dimensional vector spaces, and there's a result that says that the modules still always decompose into direct sums of indecomposable. And the decomposition is essentially unique because again, indecomposables have n dimensions ring, which is local. Now the problem is that now the indecomposables may no longer be interval modules. In fact, they may not be thin. They might have, pointwise dimension more than one. And here are a few examples. So, for instance, if you take this persistence module over the plane, which is basically an embedding of the representation of this quiver here. This is an indecomposable persistence module, and indeed, it is nothing. So you can have non-thin modules or summands with decomposition, but even worse than this. If you try to, classify all the possible indecomposable, you end up with a problem classification problem, which is basically, which is very hard. Because why? Because you can embed the representation categories of certain wild type quivers into the representation category of the plane. Okay, so this is very bad news. So how did the community react to this? That was maybe 10 years ago. People say, well, they reacted in different ways. So the first reaction one may have is to say, okay, so here are some examples where you have summands that are not thin, but maybe in applications, all the summands are thin. Who knows? So then some of us carried out an experiment in clustering. So where they took a data set. So the data set you see in the top left corner. So let me zoom in, if I can. Yeah. So the data set is in this picture here. Okay, so that's my data set. And then what they did is they built a two-parameter filtration out of this data set. So how did they do? Well, the two variables are shown here. So the first variable is the distance to the data. So basically, you draw balls at the same rate around the data point as we did earlier. And then the second variable is the co-density, which is that you filter out the data point by decreasing density, estimated density. So you start out by just the points in the highest density areas, and then you add more and more points that come from lower density areas. So that builds the two-parameter filtration. And now what's going on in this filtration is that, and then you track down the connected components throughout this two-parameter family. Now there are three main connected components. Maybe label them A, B, and C here. And what happens is that A merges with B when you go to the right. And then B merges with C when you go to the top. And then somewhere diagonally, A merges with C. So as you see, A, B, before everybody merges together. So basically, these three connected components merge independently in three different ways before merging together. And so basically, what we realize is that this, in homology, in degree zero homology, we will obtain a representation of a big grid, which will be which you can summarize as the representation of this 3x3 grid, and this representation is not. It's actually indecomposable. It's indecomposable and it's not. Okay. So yes, these non-thin summands do happen in application. And it's even worse than this, because they said so this was a work by Magnus Botnana from the University of Amsterdam. And then together with Stefan Opperman and Willy Bauer, what they decided to do is to study the representation category that you would the full subcategory of the representation category of the grid that you might obtain via these constraints. So what they realized is that when you build these two-parameter filtrations, what happens is that when you grow the balls, you can never create connected components when you go to the right. You do not create connected components, they can only merge. So what that means is that when you apply homology in degree 0, you get a persistence module over the grid such that all the horizontal maps are APs. So it's a special type of representation. So it's a subcategory, a full subcategory of the representation category of the grid. And they wanted to see how rich that subcategory was. And it turned out that it's almost as rich as the full representation category of the grid deprived of its last column or its last row, the one or the other. Okay, here it's the last row. It's actually inverted. N and M are reversed here, but no, so it's the last row. Sorry. Okay. So the result is phrased as follows. So fun of E, star is the subcategory of representations with just epimorphism horizontally. Fun of E, M is the subcategory with epimorphisms horizontally and monomorphisms vertically. And basically what they prove is that the quotient of these two is isomorphic to the representation category, the full representation category of the grid deprived of its last row. Okay, so it's as rich as this category. Now, who is this category? It's just modules that decompose into directions or rectangles like this one. It's a very simple set of. So if you take the subcategory that you obtain in clustering, you remove from it the directions of rectangles, you get something that is isomorphic of the grid deprived of its cluster. Basically, you're not gaining anything by in the special set. You just have as many indecomposables as you would have, but a slightly smaller grid. So that's the user. Now, in terms of the geometry, what happens? In terms of the geometry, you can define an interleaving distance just as you did in one parameter case. There is still a shift from her. You choose a direction. Here, the direction is just the diagonal direction. Then an epsilon shift of a module in the diagonal direction is just, as the name says, a shift of the module in the indices by epsilon. And again, there is a natural morphism from a module to this shift by taking the internal maps of the module. Now, an interleaving is defined likewise, given by a pair of morphisms in M and the shift of M and vice versa, such that this diagram appears. And the interleaving distance, again, is the phenom of the accident.
Oui, Henri.
Now, as before, the interleaving distance defined this way gives you stability, and it's still universal among all the distances that give you stability. The bottleneck interleaving distance is defined exactly in the same way. And again, because for bottleneck, we're adding more constraints, the interleaving distance is actually smaller than the bottleneck distance. Now, do we have equality? No, there isn't. The answer is no, unfortunately. We don't have equality. So for instance, if you take 3 modules, okay, in Rn, index over Rd, sorry, then the bottleneck distance, dB, is equal to, or it's bounded above, by d minus 1 times di, so times the interleaving distance. So as you can see, as the dimension of the poset increases, the bottleneck distance becomes increasingly bad, or with respect to the interleaving distance. So you can't compute the interleaving distance exactly from the bottleneck distance. Here it's a typo here. It should be inferior or equal. And now, of course, this is for 3 modules. Now, if you go to slightly more general interval decomposable modules, namely the rectangles, the real modules that decompose into rectangle summons, then things get even worse because the upper bound is 2d minus 1. And in fact, the upper bound is not known for like general interval modules, and of course for general persistence modules, we don't have them so far, so we don't know. But what is proven is that basically you cannot either compute nor even approximate the interleaving distance for general modules over Rn within a factor greater than 3 in polynomial time. So that's a result for computer scientists in the room. Basically, in polynomial time, you cannot approximate the interleaving distance by a factor greater than 3 if p is different from p. Okay, so this is very bad news because first of all, we don't really have decomposition theorems that are useful, and then our notion of distance, although well defined, is not computable. Okay, so during this, how could we react? We could say, okay, so maybe in some applications, some types of summons will show up, and maybe in other applications, other types of summons will show up. How can I determine this? Like if I consider a new application, for instance, I want to study dynamical systems, certain dynamical systems, I want to build certain filtrations on them. How am I going to determine if certain summons show up? And so, and if such, in particular, the summons that we're interested in are the interval summons. Maybe there are all sorts of summons that happen, but maybe also some interval summons, and maybe these are the ones that carry the signal. You know, so how would we detect them? How could we compute them without decomposing entirely the model? So this is a line of work that started a few years ago. The idea being that we want to build local tests that we can do on a multi-parameter filtration to test if interval summons show up. Okay. So typically, we would like results of the following form. Suppose I have a 2-parameter filtration, and I'm going to restrict it to squares like this. So I'm going to take 4 indices, okay, in my multi-parameter space, and these 4 indices will be arranged into a square like this, and I will take the restriction of the filtration to those 4 indices. If I do this, then I get a very simple, very small object that I can decompose, and I can look at its indecomposability. And can I infer anything about the big object, so the big module, from its restrictions to these squares? So to answer this question, let's look at the indecomposables of the square. And so let's look at the other right-hand quiver of the square. So here you see the dimension vectors of all the indecomposables of the square. You see that all the indecomposables are thin. And in fact, they are all interval modules. Okay. In blue, I have highlighted the intervals that are rectangles. And in red, I have highlighted the two intervals that are not rectangles. We call them hooks. And now, like a very simple observation is that the way I phrase the problem makes it trivially wrong. I mean, it makes the answer trivially no. Meaning that if you take any representation of the plane, for instance, and you take its restrictions to squares, because the indecomposables of the squares are all intervals, of course, the restriction will always decompose into intervals. But of course, the original representation was arbitrary. So of course, you have the arrow in this direction, but you don't have the arrow in the other direction. You don't have implication in the other direction. And here is just a simple example of a representation of a 3x2 grid that, of course, restricts to an interval decomposition to any interval decomposable representation of any square, but nonetheless is itself indecomposable and non-thin. Okay. Now we can't do that to characterize, we can't use just the squares to characterize the intervals, but we can use the squares to characterize the rectangles. So here's the positive result at last. If I take a representation of just a plane, this holds only for e equals 2 so far. We believe that some of the results can be extended, but so far I've only had it for e equals 2. Now a representation of the plane will be decomposable into rectangle summon if and only if its restrictions to the square are. And likewise, there is a subset of the interval of the rectangle that is even more interesting, which are called the blocks. So a block is just a rectangle that extends to infinity, either to the right and top, or to the left and bottom, or to the right and left, or to the top and bottom. These are called the blocks. And we have an equivalent result that says that M decomposes into block summons if and only if its restrictions to squares do. So what does this buy us? This gives us that if you want to, if you have an application and you build a parameter filtration in your application, and you want to know if there are some rectangle or block segments here, just have to look at restrictions to squares, and that's a test that you can easily make on the computer. And of course, you can also analyze your problem, and if you can prove that local restrictions do have squares that come up, then you will know that in your application you will have rectangle or block segments. This has found applications in TDA in the context of what we call level set persistence, and this is work that was carried out by my former student in collaboration with the global regime. Here's another approach. Now we're leaving the realm of full subcategories of representations. We're now looking at the category of persistence value, and we want to find an invariant that would involve simpler modules with a simpler structure. And a very simple idea is to take presentations. Because you can take presentations with three modules. So for instance, you replace M, you express M as the co-kernel of a module morphism. And then of course you can make sure that the domain and the codomain of the morphism are both free. Okay? In the context where M is indexed over the integer grid. Okay, and you can of course continue on this process, and you can actually take a full free resolution of your model. What this buys you is that now at every level of the presentation or resolution, the modules involved are free. So they have a very simple structure. So you can encode them easily in the computer. That's fine. Now the problem is that the maps here, the differentials, are not like so easy. In fact, they are not uniquely defined, unfortunately, even if you take minimal presentations or resolutions. And even if there is a notion of choice of basis. And so the representation as a matrix would not be unique. So even though we know that free resolutions exist and free presentations, minimal free presentations and resolutions exist in the first place if you have finitely generated modules over the integer grid, we can't really exploit the full resolution because we don't know what to do with the differential. We don't know, I mean, we could choose differential, represent them as matrices on the computer, but of course, if you give me two sets of differentials, I would not be able to tell you if they represent the same module. Okay. So what we're left with is that we can keep the summands. Okay, we can basically keep the summands in each degree, and this is what we call the multi-graded bin numbers, basically. And these are going to be unique, so we can use that as an invariant. It's not a complete invariant, but it's an invariant. So that's something that people have been doing for applications. So they use basically free resolutions and use the summands as in each degree as descriptors for the modules. Is it useful? Is it interesting to do that? Well, it depends on whether this representation is stable or not. For applications, it will be important that the representation is the invariant is stable. I will come back to this afterwards. Let me say where there was a case where the module is indexed over RD and not Z to the D. In that case, we can no longer rely on CCG, right? But there is work by Ezra Miller that tells us that you can still take resolutions, but this time the elements here in the resolution are no longer free, but they're upper set representations. So an upper set module is the indicator module of a set that is invariant under taking translation by the positive product. Okay. So here's an example of an interval module over this interval here in gray. And this guy can be represented as the co-kernel of this map from one upper set group to another upper set. And likewise, I can take upper set resolutions. And this exists by Miller's result under an assumption on M, that M should be finitely encoded. So finitely encoded means, well, the picture says it all. Finitely encoded really means that there is a coset morphism from R2 or RD to a finite coset, which is represented as these three dots connected by these three arrows. Okay. And a representation of the finite coset, so K3, K, and K2 with the maps which I did not actually define here. And such that the original module is the pullback of this representation via the coset morphism. So if your module is finitely encoded, then it admits finite upper set resolutions and upper set presentations. So you can work with those. And this is useful because if you consider, for instance, this module and you wanted to take a free resolution, you would have a very hard time because you have the continuum of generators and relations and relations and relations. On the computer, you will not be able to represent this now. But with these upper set resolutions, you can. So in this setting and in the integer grid setting, we basically switch from the persistence module to the category of chain complexes of persistence module. This is a very natural idea. Okay, and here we're basically taking chain complexes with homologic concentric degrees. So we're moving to the homotopy category, and basically you can define in the same way, like because there is a notion of morphism to homotopy between chain complexes. You can define the interleaving distance and the bottleneck distance exactly in the same way as we did in the ground abelian category. And then there are some isometry results that were obtained by Nicolas, which say that if any resolution factor from the abelian category to the homotopy category is going to be distance preserving. And then if you localize and go to the right category, you also have a resolution. And the key ingredient here is that the shift factor is basically an exact one. So it makes sense to use these resolutions because you now work in another category, but which is the isometric image of the original abelian category. So that's good. Let me spend now a few minutes about another idea, a related idea approach, which is to try to connect multi-parameter persistence to shift theory. And so the hope was the following one. So on the one hand, you have the d-parameter persistence model, which we want to study. On the other hand, there is a whole literature on sheaves on RZ equipped with the Euclidean topology. Okay? And there's a whole machinery, a whole toolbox that if we could connect the two, we could be using and import to the realm of d-parameter persistence modules. In the other direction, it could be a win-win situation in the sense that the computational tools that have been developed in this realm could be actually maybe adapted to work on sheaves. So that was the hope. So to draw these connections between multi-parameter persistence modules and Euclidean sheaves, there are some intermediate objects that we need to look at. And basically, we're going to take RD and we're going to equip it with three different topologies. So first of all, there will be the Euclidean topology, the standard topology. Then second, we're going to choose a cone. In multi-parameter persistence, the cone is just a positive quadrant here. But you can take any proper closed convex cone that has non-empty interior. Okay, so you're allowed to have a cone that's less open than this one, or even more open. It has to be proper, so it should have an angle here that is less than pi. But apart from that, you have quite some freedom to choose your cone. Now, the cone is going to be called gamma, rho gamma. V will be a shorthand for R to the D, and then gamma A will be the antiproduct of the cone. Now, the cone itself induces a partial order, okay, on R to the D, and this is the formula for the order. Basically, S is smaller than Y if the shift of the cone at X, I mean the cone base at X is included in the cone base at Y. Okay, and this is the opposite order than the one we use in persistence. So that now persistence modules are just counters from the opposite poset to the vector spaces over K. I'm going to call the category of persistence module mod of the sub and the order here given by K. So now comes another topology that we're going to put on R to the D. It's the Alexandrov topology. It's the one that is given by the order. Basically, an open set is the lower set in this order. So it's a set that is stable under taking translation. I mean, taking sums with gamma. Sorry. And the sheaves over that set are going to be, that space are going to be the Alexandrov sheaves. And this is the shorthand for it. And finally, I'm going to use the gamma topology. So the difference between the Alexandrov and gamma topologies is that now for the gamma topology, I'm assuming U, the set, has to be open in the usual topology. So the picture is the following. Here we have the persistence modules. Here we have the Alexandrov sheaves. Here we have the gamma sheaves. And here we have the sheaves, the Euclidean sheaves. The sheaves over V is the Euclidean topology. And this diagram, which was proven by by Kashimura and Shakira, basically connects everything together. Okay? So first of all, this functor here is an equivalence of categories, and there are two, and basically the gamma sheaves basically embed into both the Alexandrov sheaves and the Euclidean sheaves. Okay. Now, here is the description of the sites from which these functors originate. And this functor here is the quasi-inverse of a functor that is in the other direction, that is given by the identity considered as a continuous map from the classic usual topology to the gamma topology, which is the Euclidean topology, the refinement of the gamma. Okay, so this was proven by Kashimura and Shakira, but the question was, for us, what is the image? What are the images of the gamma sheaves, both in the Alexandrov sheaves and in the Euclidean sheaves? And this is something that François Petit and Nicolas Bercout worked out. And here is what they said. First of all, with the Alexandrov sheaves, they considered the notion of ephemeral Alexandrov sheaves. So an ephemeral Alexandrov sheaf is a sheaf that is valued at 0 on every U plus gamma, where U is an open set, usual open set. Okay. And so in the particular case of the real line, where D equals 1, basically an Alexandrov sheaf would be one that basically has 0 morphisms between S and T for any S strictly less than T. So in terms of barcodes, you may have bars that it may not be 0, but it's going to have bars that are ephemeral. They are like just single bits. Hence the name ephemeral sheaf. And now the result by Bercout and Petit is that basically there is an equivalence of category of the gamma sheaves with the quotient of the Alexandrov sheaves by the ephemeral sheaves. And this holds both in the abelian setting and in the derived setting as well. Now, the other direction, let me go back. How do we, what is the image of the gamma sheaves in the Euclidean sheaves here? Basically, it's the image, more or less, is composed of those Euclidean sheaves that have a certain condition on their microsupport. Okay, so basically, these are the Euclidean sheaves, such that the microsupport is included in what we call the polar of the antipodal of the cone. Okay, so the polar of the antipodal of the cone are the linear forms that vanish over the antipodal of the cone. Ah, this is very good. And so here again, there is an equivalence of categories between those Euclidean sheaves with distance condition on the microsupport and the gamma sheaves. So this is how things are connected. So you start from these Euclidean sheaves with a condition on the microsupport, then you send them to the gamma sheaves, and then to the non-ephemeral Alexandrov sheaves. And then you can go to the persistence models that are not ephemeral. And you get the connection this way. Now, how can you exploit it in terms of the metric? Well, once you've chosen your cone gamma, there is a notion of shift, again, given by any V that is in the cone or in the antipodal of the cone. Okay, and this shift gives rise to a shift functor with, again, a natural morphism, this time from the shift of the sheaf to the sheaf itself. And so the interleaving distance between sheaves is given by the same diagram as before, except that now the sheaves are on the left and the original sheaves, non-shifted sheaves are on the right. Okay. And there is a corresponding interleaving distance. And basically, there are 3 results in the Bercout Petit paper. The first, and these results, in a few words, they say that the functors that you see here are distance preserving. Basically, make it short because I'm running out of time. So all the equivalencies of categories that we talked about, both in the abelian and in the derived setting, basically are distance preserving. Let me just spend maybe 1 minute, if Bernard allows me, to talk about one last approach, which is much more basic, but which has actually led to real implementations. Okay, so actual experiments. Okay, so the idea is to use incomplete invariants. So we saw in the case of resolutions that we would not be using, at the end of the day, we would not be using the differentials. We would be just using the summas in each degree of the resolution. And in the same way, you can come out with all sorts of ideas of invariants that are not complete, but still that you can compute and manipulate and prove stable. And so very simple ideas came out. So one of the very first ones was to use the dimension vector or the Hilbert function of the module. So basically, this tells you at every index of R to the D, it gives you the dimension of the space at that index. Okay, so it's a very simplistic invariant. Of course, it's not complete. So here's an example for a 3x3 grid. The invariant would look like this. It's a function over the indices in the grid to the integers, to the natural numbers, actually. And so it's 1 when you have light gray, 0 when you have white, and it's 2 when you have light dark. Okay. Okay, and some people have derived some like further constructions from this invariant. I mean, well-known objects like Hilbert series or Hilbert polynomial have been leveraged in work by Harrington and Al to actually devise practical invariants used in like real applications. Here's another slightly more elaborate invariant, which is the rank invariant. And this one was really proposed for use as early as the very first paper on multi-parameter persistence, which was back in 2009. And this one, instead of encoding just the pointwise dimensions, it encodes the ranks of all the internal maps of the model. And from this rank invariant, you can two descriptors for the module have been proposed. The first one is the so-called fibered barcode. The fibered barcode basically consists in building a function that, given any line with positive slope in the plane or in R to the D, will output the barcode of the restriction of the module to this line. Indeed, the line is one-dimensional, and therefore the restriction is a one-parameter persistence module, so it has a well-defined barcode. And so, given any line, you can always output the bar. You can always compute the barcode of the restriction to that line. So this is a very simplistic invariant, but it actually was implemented in a very nice piece of software called Rivet, which people are actually using. And so you can, you have you have a window, and in this window you see first of all not the rank invariant, but you see the Hilbert function, and then you can choose, you can move your line around, and as you move the line around, you see the barcode of the restriction evolve. And it's a very nice tool for data exploration. It's very nice. Again, it's based on a pretty weak invariant, but still, it's a nice tool. You might, people might ask the question, well, is this invariant complete? The answer is, of course, no, because it's not more, this invariant is not more powerful than this one. It's actually equivalent, and of course, the rank invariant is not complete. But still, it's a nice invariant. And there's another invariant that was recently proposed, which is the so-called sign barcode. It basically takes the rank invariant, and if you remember, in one-parameter persistence, you can always, like the decomposition theorem, you can always express the rank invariant as the rank invariant of the direct sum of interval modules, of interval models. In higher dimensions, you cannot always do that, but you can always, on the other hand, represent the rank invariant as a function, as the difference of two rank invariants of rectangle decomposable modules. So here's an example. This was like our working example with an indecomposable module that is not thin. In fact, this indecomposable module has a rank invariant that can be expressed as the difference between the rank invariants of these two direct sums of rectangle modules. And where are the rectangles? In blue here, you see the rectangles whose positive slope diagonals are given by these bars. So there's this rectangle over here. There's a rectangle that is long and thin like this. There's this rectangle over here. And then in the red parts, there's one rectangle here and one rectangle here. And you can prove that you can always express the rank invariant this way, and there is always a unique minimal way to do it. And so this gives us a notion of barcode for multi-parameter persistence modules, except that it's a sign barcode where each bar has a sign. And then with that, you can do all sorts of things in practice when you do a data exploration or machine learning. Again, this sign barcode is not more powerful than the rank invariant itself, which is a very neat invariant. But nevertheless, it's extremely useful. I mean, it's in practice, it's useful because we do have tools to compute it efficiently and to manipulate. Let me skip just the example to show you an application in clustering, but let me move on. Well, if you give me just 1 minute, I don't want to be taking too much of your time. Otherwise, we can talk about it later.
We started a little late. So
Okay, no problem. So if you have access to the, I mean, you sent out the slides. So I mean, people can look at the application. The idea is just to say that in the example in clustering that I showed earlier, where we had this indecomposable that was not in, basically we're able, by the sign barcode, we're able to track down the lifespan of each of the 3 main clusters, basically A, B, and C. So in the barcode, which is the sign barcode, which is, you see here, you see the lifespan of A, the lifespan of B, and the lifespan of C. So it's good enough for this application. To conclude, let me just say that, as you may have seen now, the question of multi-parameter persistence can really be attacked from different points of view. What I would recommend or ask to any of you who might be interested in contributing is that whenever you come up with your own invariant, you have to keep in mind these 5 aspects. So, of course, you want the invariance to be as rich as possible. You want to capture as much of the structure of the module as you can, of course. But on the other hand, it's always a trade-off between richness and efficiency of computation. If your invariant is not computable, then I will not be able to exploit it. Okay. We also want it to be stable because otherwise, we will be having a hard time doing any kind of statistics with it. And of course, ideally, your invariant should be interpreted for data exploration. And finally, what's missing is a practical evaluation. For now, until now, we still don't know what is the real potential of multi-parameter persistence. We haven't really used it. I mean, it has been used in some real-life applications, but it has not been yet clear that it's clearly better than one-parameter persistence. And this is something that we must. All right, thank you. Sorry for going over time. I'll be happy to answer questions.
Est-ce qu'il y a des questions? Other questions? Yes.
Plus en détail, oui. Pour définir la distance, il faut choisir.
Une direction. Voilà.
Comment?
C'est la direction, c'est ça?
Ouais. On peut prendre des boules, on peut combiner par une boule. Attends,
Alors,
non, il n'y a pas besoin. Comment? C'est là pour tous les éléments. On a fait que c'est pour les questions constructives, en convolant par des boules. On dit, ah, le choix de gamma. Si tu as un gamma, tu peux remplacer les boules par une direction. Oui, par une translation d'une direction. Si tu as un gamma, tu peux prendre une boule, tu peux les directions. Quel est l'intérêt des faisceaux, comment ça s'appelle, éphémères dans la pratique? Parce que moi, je connais la géométrie, on a fait ça il y a 40 ans, c'est ça. Mais comme disait Alexandrov, ça rajoute les faisceaux éphémères. J'ai l'impression qu'ils servent absolument à rien.
alors, dans les calculs, tu ne les verras jamais apparaître. Ou alors avec probabilité 0, quoi. Après, c'est toujours la même question, c'est-à-dire que tu prends des mesures sur un système physique. Alors évidemment, si tu fais des hypothèses sur ton système physique, peut-être qu'en fait, tu n'auras jamais d'éphémère sous-jacent, mais bon, ça va vraiment dépendre des hypothèses que tu vas faire sur ton système physique. Peut-être que les éphémères sortiront dans certaines situations. Pas dans tes calculs, mais par contre, dans l'objet, dans la réalité terrain sous-jacente. C'était tout l'intérêt de regarder les effets. Par exemple, si tu prends la distance à un compact, si tu ne fais pas d'hypothèse sur ton compact, évidemment, tu vas pouvoir avoir un module qui va avoir une partie des sommandes qui seront éphémères. Par exemple, après, si tu commences à dire que ton compact il a telle et telle de régularité, à un moment donné, les éphémères vont partir. Mais par contre, si tu ne fais pas d'hypothèse, bah, tu pourras effectivement avoir des éphémères dans le module.
Pour mettre en valeur, il y a une chose qu'on a faite avec les chevaux, pas du tout à la mode dans la communauté, c'est de traduire tout en dérivés, tout mettre en catégories dérivées. Il y a des phénomènes qui sont vraiment liés aux catégories dérivées qui disparaissent.
Non, je suis d'accord. Alors là, j'ai cité les théorèmes essentiellement en abélien, c'est vrai, c'est pour des raisons de temps, mais en fait, à la base, les théorèmes d'isométrie sont énoncés en dérivés et après, les corollaires sont en abélien. À la base, ils sont en dérivés.
Yes, there is a question by Jean-François Mascari.
Oui.
Please unmute yourself. We can hear you. Should be able.
Bonjour. J'aurais une petite question de caractère général. Est-ce qu'il y aurait un intérêt de considérer non seulement les faisceaux comme outil mathématique, mais aussi des cofaisceaux? Donc, avoir exploité un peu tout ce qui est dualité entre faisceaux et cofaisceaux. Les gens encore plus catégoriels du sujet.
Alors, là, je ne veux pas dire de bêtises. Je sais qu'il y a certains travaux qui sont énoncés, qui sont écrits en cofaisceaux dans la communauté. Après, je ne saurais pas te dire, là, ça dépasse mes compétences, de savoir si vraiment il ne pourrait pas être réécrit en faisceau, honnêtement.
D'accord.
Si on prend le bon langage, c'est pareil.
Oui.
Et c'est un langage qui est un peu lourd. Il est en termes de données et équivalence de catégories entre faisceaux et cofaisceaux. Et dans le cadre ultra-général.
Ok, merci.
Est-ce qu'il y a d'autres questions parmi les participants sur Zoom? Are there questions from participants on Zoom? Please just unmute yourself. Il y a d'autres questions. Est-ce que les upper-set resolutions sont toujours bornées à gauche ou on avait dans les exemples ça semble.
Oui. En fait, il montre qu'on peut toujours en trouver des bornées à gauche. Si le module est comment est-ce qu'il appelle ça déjà, pas infiniment encodé. Donc le module soit infiniment encodé. Hein, voilà. Donc, il faut qu'il soit le pullback, une représentation de cette. Il y a vraiment fini de fait. Et dans ce cas-là, effectivement, il y aura des résolutions par upper-set modules qui sont finis. Il y a même aussi il y a des résolutions minimales aussi. Voilà, oui, c'est ce qu'il m'a dit. Je ne suis pas sûr que ce soit publié, ça. Je ne vais pas dire de bêtises. Oui, ça paraît vraiment un outil assez naturel dans ce cadre-là, parce qu'on a envie de faire un peu comme on fait dans le cas discret ou dans le libre. Simplement, on ne peut pas prendre c'est pas raisonnable de prendre des résolutions libres comme ça, l'équivalent d'un module indexé sur un module, d'un module indicateur d'un cadran comme ça, là c'est un peu l'équivalent, c'est le module indicateur d'un comme ça.
Est-ce que le théorème sur la décomposabilité en bloc, je vous une traduction, oui. C'est vrai aussi en discret? Z2?
Que je dise pas de bêtises, oui, je crois que c'est vrai aussi.
Et quels sont les. Oui, c'est de la pure théorie des représentations.
Alors, en discret, tu peux le faire vraiment à la main, je crois. Moi, c'est la manière dont je le trouve, mais bon, c'est avec mon niveau de maths niveau humain, disons, avec des maths niveau humain. Après, si tu veux le faire dans le cas continu, c'est un peu plus compliqué, on a utilisé des filtrations fonctionnelles. Donc, voilà. Et on avait discuté avec Bill Prolet pour savoir s'il n'y avait pas moyen de faire plus simple. Et on n'a pas trouvé. Alors, on a un papier qui est très, qui est très technique et pas très intéressant à lire.
Merci encore pour ce tout le monde est invité à participer au dîner avec le conférencier. Si vous ne souhaitez pas, merci de nous signaler. Gilles, on va la zigothèque, on a une réservation pour 7h. 19h. À la zigothèque. Donc la zigothèque, c'est 15 bis rue de Tolbert. 15 bis rue de Tolbert. On peut y aller ensemble, on se donne rendez-vous à 7h-10 en bas.
Ouais, c'est la 7e année. Et toi, du coup, son poste, Alex? J'ai l'UR. Ouais, t'as eu D'accord.
Alors, tu n'es pas encore parti en Chine.
Non, je suis